Good morning. It's my pleasure to present you our work on the assessment of the durability of airtightness products in laboratory controlled conditions. I will present the development and the definition of the experimental protocol. I am Andrés Litvak. I am an engineer at CEREMA. I've been working on airtightness for more than 20 years. And I've been working on collaborating project and with French centers. Today I have a slight technical problem, so Valérie will show that I've been working in the project. Will show the slides. This paper was presented at the last conference, AIVC conference in Ghent, and do not hesitate to contact me to get the article for further details. As Valérie explained, this is part of a research project, Durabilitaire, and I'm presenting you the task number 3 that dealt with laboratory conditions, and this was done with our partners, Rescol, which is a French technical center and a research company based in Bordeaux, in France. The study is Durabilitaire is a 3-year, four-year work that aimed at improving our knowledge on the variation of buildings' envelope airtightness through on-site measurements and accelerated aging in laboratory controlled conditions. Valérie presented the state-of-the-art review on the laboratory conditions in this seminar. She and my colleague Bassam Mujaled, they presented the preliminary results on previous AIVC webinar, so you should have the overall overview of the project by attending both seminars. The state-of-the-art showed that there is no standardized protocol to characterize in laboratory controlled conditions the durability of the product assemblies regarding airtightness performance. So as a matter of fact, due to the diversity of airtightness products, it's difficult and even perhaps impossible to define an accelerated aging universal protocol, as Valérie mentioned it, that would be equivalent to a known amount of years of natural aging. So in the light of this work, we observed that the results of the aging tests vary from one study to another, as Valérie shown us. One of the main reasons is that the protocol is not standardized, but nevertheless, the following general conclusions can be drawn. First, implementation has a strong impact on durability. It's regarding to the question that was asked to Valérie. Products do not have the same reaction under normal conditions as when they are subjected to extreme conditions, temperature, humidity, or pressure. The standardized procedure for the aging of sealant is lacking to characterize products and especially assemblies regarding airtightness performance, and we will focus on the assemblies of products and not on the products themselves. And the importance is the assembly of products put in situation. And we'll also look at the product performance. Valérie, you might come back to the previous slide, please. Yeah. We might look for the product performance against conventional test procedures in order to assess their performance in terms of airtightness. And well, the aging must be consistent with the loads and the position of the air barrier. So our methodology, we can go to next slide. Our methodology consisted in defining the exposure conditions of relative aging tests through thermal, humidity, and pressure variation cycles. And we define a protocol by developing an experimental chamber, by choosing the representative samples of assembly products, and defining the accelerated aging conditions. So we can go to next slide. Thanks. The environmental chamber consisted in an accelerating weathering chamber, which is, you can see here, it's in 1 meter by 1 meter by 1 meter, so one cubic meter. A pressure test bench for differential pressure exposure and airtightness measurement, and a sample holder between both enclosures. So here it's represented as in the illustration. The frame of the sample holder and the differential pressure bench constitute a single independent machine that allows to perform wind cycles and airtightness measurements between minus 250 pascals and plus 250 pascals. We just stay, okay. We created a differential pressure on the sample by positive and negative pressurized air with air mass flow controllers. Pressurization created the conditions for both the exposure to wind exposure and the airtightness measurement test. We designed the technical specification of the pressure test bench with a view to get the best compromise between a good signal stability and a fairly large user range in order to test the various implementation solutions and to maintain a controlled reactivity and a sufficient flow rate to carry out cycles with imposed frequency. And last, tightness, repeatability, and reproducibility tests were performed. So this was the presentation of the exposure chamber. The methodology, we defined a test as 4 successive cycles applied one after the other with intermediate measurements to control the evolution of airtightness between each cycle. So we designed 4 weathering cycles in order to accelerate the aging of the samples. So we can go next slide. And with for the cycle number 1, we apply the following cycles to the exposure chamber: 60 degrees centigrade and 50% of relative humidity for 21 hours. Then we did the airtightness measurement, and then we applied a pressure load of wind cycle of plus or minus 50 pascals for 200 cycles for 2 hours. So the duration of the cycle was approximately 24 hours. For the cycle number 2, we applied the following cycle. So we call it the 4-season cycle, with a winter with minus 10 degrees Celsius for 24 hours, with a spring at 15 degrees centigrade and 60% of relative humidity at 24 hours. The summer cycle at 30 degrees Celsius and 45 relative humidity for 24 hours. And the autumn at 5 degrees centigrade for 24 hours. And then we had a stabilization period for 12 hours, and we ended the cycle with a new measurement of the airtightness. So the whole cycle was approximately 4.5 days. For the cycle number 3, we applied pressure cycles from minus 250 pascal to plus 250 pascal by 50 pascal steps. We did 8-hour cycles 3 times, so for a total duration of 24 hours. And for the last cycle, we applied a temperature increase of plus 1 degree centigrade by minute until the temperature reached 180 degrees centigrade. And if no leakage appeared, then we applied a constant temperature of 180 degrees centigrade for 1 hour. So now for the definition of the samples. So it's samples made of assembly of products. The 3 types of assembled products as treatment of airtightness of the joints between windows and walls were chosen as samples to be tested. The first sample is the assembly of an expensive weather seal foam tape installed between the frame and the opening of a wooden carpentry. The selected foam tape has an operating range of 5 to 11 millimeters. So as you can see in the picture, the sample holder allows the installation of 2 samples in parallel with both operating range. The second sample is the assembly of backup strips and filled up with mastic as a sealant, implemented between the frame and the opening of a wooden carpentry. The selector backer rod has an operating range of 5 to 11 millimeters, and a fixing coat was applied to the wooden surface before implementing it. And this sample also allows the installation of 2 samples in parallel, as you can see in the picture. And last, the third sample is the assembly of a membrane taped and stapled on the opening of a wooden carpentry. 2 identical membranes were implemented in the sample holder, as you can see in the picture. So the first result that we collected, we could first observe that the 3 samples had very different ranges at airflow rate permeability for the initial measurements before the aging test begins. Here you can see that in this diagram, in red dotted lines, we have the maximum compensation capacity in airflow rate of the pressure bench. And we can see that for this, we were at the limit of the measurements for the sample number 1. In red plain lines, we can also observe that the airflow measurement precision of the bench, and we can see that we were on the limit of the sample number 3. So, and another comment that we had, that these results showed no trend on the impact of the pressurization mode, I mean positive or negative pressure, with the corresponding air permeability flow rate. So we can see that we have very different ranges in air permeability in the 3 samples, and we focused on the sample number 2 that allowed us to see the main results for our work. So you can go to on this slide. The air permeability flow rate was measured over the full range, minus 150 pascals to plus 150 pascal for this sample. And for each cycle, the results were compared with the initial airflow rate results and showed the following traits that I will comment. We had an improved air tightness between initial measurement and the test number 1, from the cycle number 1, in the top left diagram. This improvement was explained by the moisture saturation and therefore the expansion of the wood frame. So this is intuitively these first results. Then, as for the first cycle, on the cycle number 2, on the top right hand, we found that cycle number 2 showed an improvement in air tightness due to the moisture saturation of the wood frame. We could also observe that test number 2 did not have any impact on results of test number 1. The first degradation of the air tightness was observed on the test number 3 in the back left diagram, which was the first to deteriorate the air tightness of the sample. The increase of air permeability flow rates were found to be in the range plus 3% at minus 150 pascal to plus 7% at plus 10 pascals as compared to the initial test. And then the rupture for the last cycle occurred after 140 minutes, corresponding to a temperature of 120 degrees. We observed a sudden drop in pressure and saturation of the flow. The fourth measurement was performed after sample stabilization and showed a significant impact on the airtightness for the sample for positive pressure, with a difference from minus 22% to 29%, from 10 pascals to 150 pascals for positive pressures. For negative pressures, the increase was found to be less important, from 0% at minus 150 pascals to plus 18% at 10 pascals. For the sample number 3, we had a sample that was very airtight. It was very sensitive to pressure variations, both positive and negative. So we didn't notice any significant deterioration of the air permeability flow rates for the first 3 tests of the cycle, and for the breaking test, the last one, the rupture occurred at after 40 minutes at a temperature of 60 degrees. As a conclusion, I would say that the 3 types of samples made of assembled products as treatment of carpentry airtightness showed very different results according to the maximum compensation capacity of the air permeability flow rate of the bench. We were limited by these specifications. The choice of the sample made us that the sample number 1, the expensive weather seal flow foam, appeared to be too porous for our equipment, whereas sample number 3, with the adhesive and membrane complex with staples, appeared to be too airtight. So we could draw some conclusions, some interesting investigations from the sample number 2, with a rupture that occurred at 120 degrees Celsius and showed a significant decrease of the airtightness of the sample. As we saw, we measured the slight deterioration after cycle number 3, up to 7%. Nevertheless, we could not draw any definitive conclusion about the artificial aging of the protocol to the elevated temperature of rupture. Remember what was mentioned by Valérie on the experimental conditions of test for this test may probably contradict the statement that never test products beyond their real-life exposure conditions. The improvement airtightness during the aging cycle of the second sample is probably due to the humidity for the thermal creep test and the weathering test. Thus, we recommend to use inert materials as sample holders for future work. Here, the wood may have played a significant role. And this was confirmed by the field measurement results from task 2 that was presented in the article by Bassam Moujaled on the measurements on wood structure houses that tend to improve over years. We explained that to the expansion of the wood with the humidity that would clog the leakage. So as a last conclusion, the wind exposure for test number 3 of the aging cycle on sample 2 showed a very moderated increase of air permeability. We think that the duration of this cycle was too short, and that the exposure duration of at least 1,000 hours, so approximately lead to a duration test of 1.5 months, should be necessary. We are working right now on defining future works, and we plan to investigate a better compromise between signal stability, usage range, and control reactivity on airflow of the bench, and exposure protocol conditions. That might be a key point. So Thank you very much for your attention. I will be very happy to answer to your questions. And just to let you know that there is an internet website which is in French. It's www.durabilitaire.com. And don't hesitate to visit this website, and you will have the opportunity to download all the articles and the presentations. Thank you.